this talk here. I want to thank Aaron Schlichting and Brandon Price from STEM who actually invited me and set up the whole program. And so I'm really excited to be here. As Susan said, I'm coming from the US Geological Survey in Menlo Park. We're a federal government research institute, so of course we've been shut down too, but hopefully that won't affect the talk too much, or shut down for the furlough. But we're an independent research institute, so we don't advise on political decisions that come out of that. We really just report on the science. So the topic I want to talk about today, induced seismicity, obviously has a big political pull behind it, and especially for California residents, we're probably a little bit more alert to induced seismicity because we use two larger type seismicity to begin with. So I'll talk a little bit about the science. I'll also go over how I got to a STEM type career and why I decided to study earthquakes and as a student and now work as a researcher. I'll talk a little bit about my particular research topics, which are intended and unintended earthquakes, and I'll explain more clearly what that is, and motivate the whole concept in more detail beforehand. Aaron sent out a really nice flyer, and I really appreciated the advice of giving advice to the students on if you're interested in one of these careers, or in particular in earth sciences, or geophysics, or geology, what types of advice I have to give for that, and in particular what types of classes may be interesting for you to take now. And I'll also talk to you later on about some opportunities within the USGS and similar institutes in the Bay Area and in California, where you as a student can get involved with paid and or unpaid internships and gain some experience and see if this is something for you. And of course I'll entertain questions from you guys. If you guys have a burning question before the end of the talk, feel free to interrupt me at any point, okay? So my journey to this sector, you can probably tell I have a bit of an accent. I haven't gotten rid of it. I'm from Germany originally. I graduated high school. And the German system is a little bit different than the US system because you have to decide what you're going to do right out of high school. Luckily, schools are free, so it's not quite as much of a financial burden. But I went to law school, and it really got me nowhere. But I had the opportunity in 1997 to enter college in Hawaii. And it was only going to be for a short time, so at first, but this is now, 17 years later, 20 years, 16 years later or so, didn't quite work out the way I planned it. And there, I shared, this is a picture of me actually in my first year, and yes, we were the Rainbow Warriors and are again now. And so I shared maybe some of the same struggles that some of you have, being ESL students, especially in STEM. So when I actually met one of the current communication professors at Cañada, my first sentence to her was, I don't understand a word you're saying, probably with an even stronger accent than now. However, I got over my struggles, luckily, and so this is, if you don't know, Professor Kaven from Communication Studies. And she seemed to be pretty stoked that I got over those two, at least judging from that picture. But I then, while I was in Hawaii, I really liked it and got interested in geology and geophysics. And it's easy to get interested in geology and geophysics if you live on a volcano. So this is actually on the Big Island with lava flowing onto the surface there. And you can actually walk up at times and poke it and throw pennies in it. They burn green, and it's really fun. And it's really hot, which you can maybe tell from my somewhat not happy expression. So eventually, though, I wanted to really understand how, for example, magma comes to the surface. And in general, that happens along faults and fractures. So for my master's thesis, I actually get involved in how you model faulting on a volcano, how that allows for magma to travel up to the surface and get a better understanding of how the plumbing system of the Hawaiian volcano at least works. And at that point, I already got deemed by my colleagues in the geology department as an intended geologist because you do a lot of modeling. And so this work then I actually did for my master's thesis and then followed up with a PhD at Stanford, where the sort of fieldwork component got smaller and smaller and more modeling. was interested, became part of what I was doing. So there I worked extensively on how faults slip, especially faults that aren't, as they're often approximated, flat surfaces in the ground, but some that actually are a little bit more complicated and maybe better represent what's going on in the surface. So these are two representations of the same fault. This is the Joshua Tree Fault. You'll see a couple figures of that later on. And it shows in the colors the slip distribution of an earthquake prior to the 1992 Landers 7.2 earthquake in Southern California. I'll go into somewhat more details there. In 2009, I started working at the USGS here in Menlo Park, and I've stayed there, and it's a great place to work, and if I can extend my stay there, I certainly will. And so that's what brought me here today. But the other things, so I guess what I am doing today looks a little more boring. So some of you from CIS may recognize this. So this is kind of what I do on a daily basis now, at least a big portion, which is programming. But I enjoy that part. So you guys are well prepared from probably all disciplines instead. So I wanted to give a little overview of what types of classes I took, because obviously you guys are probably most interested in, if you are interested in a STEM career, what types of classes you have to take. So obviously geology and geophysics, but I took a lot of mathematics classes, and you guys obviously have a lot of those at your disposal now. Calculus, partial differential equations, linear algebra, applied mathematics, and then continued on with more engineering, numerical analysis, types of classes doing masters and my PhD work. And then because you really have to understand how to then use those equations that you learn and do something useful with it, obviously a lot of programming that goes along with it, and I'm sure a lot of you guys are doing that now. So one advice that I got from a professor during my master's was that to really be a good programmer, you have to choose one language, and I don't think that's true at all. I think nowadays knowing more than one is absolutely necessary, and they're close enough now that you actually have a lot of carryover between languages. So don't follow that same advice that I got. So that, needless to say, I had to take a lot of courses after the fact. So my current research as a postdoc at the USGS in Menlo Park involves trying to understand how faults form in geothermal reservoirs. So one of the components of that is trying to figure out exactly where earthquakes happen, identify faults that cause these earthquakes in clouds of seismicity or earthquakes, and then develop numerical methods for fault slip that is modulated by fluid flow. In these geothermal regions, obviously, fluids travel and produce the heat, but more detail on that later. The other aspect that I'm working on now is monitoring earthquakes and modeling fluid flow and deformation at CO2 sequestration sites. So for those of you that aren't familiar with this, CO2 sequestration is a technique that's hailed as one of the possible solutions to CO2 increases in the atmosphere by capturing CO2 at sources, say oil or gas fired power plant, and then injecting it underground and storing it underground to not let it escape into the atmosphere. And so there, the problems are a little bit different, but not that much different. So the work I'm doing there is do high precision earthquake relocations and try to model the flow of CO2 and water combined. It's a little bit more complicated. We probably don't need to get into details of that now. And what I want to focus on mostly in the later part of the talk is the initial work in geothermal reservoirs. But I want to step back a little bit and introduce the broader issues that our research project, Induced Seismicity, actually deals with. And to motivate that, I want to show you guys seismicity, earthquakes for 10-year periods in the mid-continent of the US. So the blue circles here are earthquakes. These particular ones are from 1970 to 1979. The sizes of these circles are relative to their actual magnitude. And the distribution is pretty varied. You have a lot of them in what's called the New Madrid fault zone, this cluster on the eastern part of the map, and some up in Denver, in Colorado and in the Denver Basin. I'll talk more about where exactly that is. And then obviously some in Texas and so on. So if you look at the same 10 years, now 80 to 89, you see more or less the same distribution of events, about 200 or so events that can be detected, and those that can be detected are magnitude 3 or larger. And so if you go 90 to 99, just about the same picture, not much changes. The rate is roughly 21 or so earthquakes a year in this particular region. And now if you go to 2000 or 2011, all of a sudden you have 524 earthquakes in the same time, 10 years. And most of them are located in Oklahoma and very closely spaced, all in Oklahoma, basically on top of one another, in southern Colorado and some in Texas. And so this obviously is a huge change in the rate of seismicity, or the number of events that happen. And if you plot this up for this particular region, what's plotted here is just the cumulative number of events, and then subtracted from that the sort of 21 events per year. And in 2000 or 2002 or so, that rate increased dramatically. So that's certainly something that is worth looking into further. And so if we try to relate this to the actual geology or the economic geology in that region, we're going to look at some of the actual regions that you see. So where we saw a lot of the earthquakes were in Oklahoma, which is the Anadarko Basin. These purple and pink portions here are actual shale plays or shale reservoirs. In Texas, you have the, in Texas, you have the Barnett Shale, Eagle Ford, and so on, and then you have the Denver Basin in Colorado and the Raton Basin down here. Another one that you may have heard about is the Bakken Shale in North Dakota, which has also been explored quite extensively. That's the question.
Would you say it's no coincidence that these areas where there's a lot of shale, because of hydrofracking, that would contribute to the seismic activity?
Great question, and wait one more slide, and I'll show you something that may or may not convince you. So these are the regions where shales are in play, and for one of the regions, the actual Barnett Shale, which is very similar to these other regions in Colorado and Oklahoma, when you look at these, this is a number of wells per year, and on this also are a couple important dates that indicate the improvements in production and exploration techniques. So you see that it was a fairly low number of wells in the beginning, up to about 97, and then steadily increased. And so 1999 refraction simulations is sort of the predecessor to what's hydrofracking. And then the real advent, or the real technological advancement was horizontal drilling. So usually you drill a well, it's more or less straight down. But at that time, the technology improved enough that now we can steer well bores for kilometers away from your well bed and actually target particular reservoirs or layers of rock and drill through those. And so these techniques were absolutely necessary to start fracking, and we'll get into the details of that later on. So there clearly is, and I'll show this plot here, the increase in seismicity in this general region certainly is connected to or similar to the increase in well bores or boreholes drilled and producing wells available in a particular shale field. Now, the one thing I want to allude to, though, if we look at some of the big plays, and the Bakken Shale is one of the large ones that's being explored now up in North Dakota, here the same techniques are employed, but you don't see any earthquakes that are registered magnitude 3 or higher. And so clearly the problem is related to a lot of these new production techniques, but it's not quite as simple as saying this is the cause of all of it. There are different geologic environments that don't produce the type of seismicity we see in Oklahoma or Texas. So this is sort of the background I want to give. And so clearly oil and gas production is one of the contributors to earthquakes that are man-made. Geothermal energy production is another one. CO2 sequestration, as I mentioned, is one of my research field, has produced very small seismicity. And another one is dam impoundment. Actually, one of the largest induced seismicity events in Koina, India in 1967 produced a 6.2. Because you load water on top of a fault that's already there, and you produce an earthquake that may or may not have happened regardless, but you certainly accelerated the process of getting to that critical state. So on the right here, there's a few recent earthquakes that are related to, or may potentially related to man-made activity. And the Prague, Oklahoma is how they call it there. Trinidad, Fracking, all of those large ones, 4.8 to 5.6, are near exploration and production wells for oil and gas exploration. There's quite a bit of dispute of what's actually going on and which wells are responsible for it. As you can tell, Oklahoma is a pretty oil-heavy state. And another one is this Timpson, Texas one. This is a really interesting one. This is actually related to storage of gas in an old salt dome. The only one that is directly related, and directly I'll explain a little bit more detail what that means, directly related to fracking is this Horn River Basin earthquake in British Columbia, which is at 3.6. So of those events, oil and gas exploration can produce large events, 5.6 recently. Geothermal energy production has produced in California events that are 5.2, 5.1 or so in the coastal geothermal field. The Geysers geothermal field just north of San Francisco has some earthquakes in that magnitude range also. And CO2 sequestration is not a big issue currently, but the technical implications of that is if you have earthquakes, the actual sealing layers that seal CO2 or that trap CO2 down low, if they're disturbed by earthquakes, you may not need a very big one to break the seal and really risk the success of these sequestration projects. So I want to give a very brief overview on what actually takes place as far as the simple models of earthquake nucleation. And so, as most of you know, stresses or forces in a continuous body that aren't on a surface but act on neighboring particles, if you will, are present in the Earth at any point. So this is these SV, which is a vertical stress, and then an SH or horizontal stress. These are acting on, in blue, this particular fault where these stresses can act on as forces, just like you may know it from your physics classes. You have a normal force, the sigma n, and the shear force. And slip on this particular fault is resisted by the friction on the fault. And the friction on the fault is mu parameter. We have large ranges of those. It's difficult to actually know what those are at particular locations, but we have a somewhat decent understanding of how that works. So in induced seismicity, where you're adding fluids or extracting fluids from a particular portion of the crust where you may or may not have faults, you're changing this pore pressure. And this pore pressure essentially changes the critical state or the normal force that is acting on the fault in particular, so this pressure. So if you think about, you have a fault, you increase the pressure, fluid pressure, you slightly move those adjacent walls apart from one another. You don't quite move them apart, but you decrease the actual clamping force that's on it. And so once you get to this critical shear traction, then you have an earthquake. And so earthquake sizes, how are those calculated, and why do we care about what is at play in determining those? If you have two surfaces that slide past one another, so here's a very simple figure describing this. If you have the area, the fault area, and the slip area, plus the shear modulus, which is a material property of the rock, much like we have in steel or any other really material, you get a seismic moment. And this moment can be turned into something that's similar to the magnitudes that are recorded or reported in the press. These magnitude 7.9, for example, for the 1906 San Andreas earthquake is due to the fact that the San Andreas fault ruptured over roughly 300 miles. And that's an order of magnitude larger than, for example, the 1989 Loma Prieta earthquake that interrupted the local World Series. There's a 6.9 that only ruptured on a fault roughly 25 miles long. So it's really the area of the fault, or the available fault that's close to failure, and the area of that fault that can't fail, that determines how large an earthquake can be. So we're interested in finding where those faults are, where we should and should not inject fluids, and how far away we should be from that to avoid setting of earthquakes. So, excuse me. So the general processes at play then in any of these man-made induced type events is that on the left here, you inject fluids in a well and you hit some permeable layer, and this permeable layer has some communication with the nearby fault that's large enough and that's close enough to a critical state where large events can happen. Similarly, and this is more representative of what happened at the Koina, India earthquake, you have a fault deep down below that you don't know and didn't know about. You change the mass or the volume above it, so you load the fault more, and you set off a particular earthquake that you didn't anticipate. So it's really the changing in loading conditions, whether it's your shear stress or shear traction, shear force, your normal force, or your pore pressure that acts in conjunction with those. So both of these scenarios are probably at play in most places, but discerning which ones are important is quite complicated. And so I know this came up already, the fracking question. So for fracking, what's done, again, the technological advances were that you can horizontally drill into very thin layers that contain hydrocarbons, oil and gas. And you drill into those, you plug the hole, you pressure your well, you perforate the pressure, and then you create all these little fractures. So the actual surface area of a fracture or fault is relatively small. So the events, the earthquakes you produce with that are actually quite small. The largest one, again, was at 3.6 or so in British Columbia. The problem is you produce or you use a lot of water that you inject with or without chemicals or proppants that keep these fractures open. And that water has to come back out. It's a byproduct of oil and gas production. And that's true for non-fracking oil and gas production also. So that water comes back out and has to go somewhere. And in most places, it's injected below the regions where you actually frack a particular shale or limestone type reservoir. And there you may or may not have a fault. Again, that's close to failure, and you may or may not know how large these faults are. So there is an associated risk with fracking of induced seismicity, and it cannot be ignored. So now I want to come to sort of my favorite, the intended earthquakes. And have a much better reputation in the public too than fracking-induced earthquakes also. And these are in geothermal areas. Geothermal areas, places where you have high temperatures, shallow to the surface, often associated with volcanic regions. The geysers is one example north of here. There are several in Nevada and Southern California. And what the problem with those rocks is that they are really tight rocks, and the only permeability you really have is through fractures and faults. So what you're trying to do is you're actually trying to inject at a pressure high enough to either create faults or stimulate small faults that are already there, get those to the critical state, but because there's so many and it's a smaller region over which they can rupture, you create small earthquakes and you increase permeability along these fractures. And the reason you increase it is that these aren't perfectly flat surfaces, they're corrugated, they're rough surfaces. When you slip those adjacent walls now don't quite fit together anymore, so you create permeability in those. And so you actually are changing that, and you're increasing the heat yield or the electricity production you can do with that. So those are actually the earthquakes you want to get. There are some rather large ones that have happened in geothermal regions that may or may not have happened without the production. And one example is 5.2 at Coso in the 1990s. Luckily, Coso is out in southeastern California on a Navy base, so nobody complained. There's some that are certainly nuisances to the residents near the geyser geothermal plant north of here. They have magnitude 3 earthquakes quite frequently, and those, as you guys probably know, can be a bit of a nuisance. But those ones we actually are trying to understand better to increase our electricity gain from these reservoirs. So the real challenges in understanding this problem in any of these settings is to know where exactly small earthquakes are that may tell us about the locations of larger earthquakes before. or if there are larger earthquakes, larger faults, they often have a series of aftershocks, after events that help us identify exactly the location and geometry of those. So we want to know the fault geometry well, know how large they are, how extensive they are, and then obviously we need to know the stresses in the crust, and this is quite difficult because you need to drill well bores, you need to do a lot of testing in those. These wells are really expensive, and you can't get trucks, these drilling trucks out because they're all making production wells in the central US right now. You need to know about the material properties, friction, permeability, rock properties, and so on. And you need to know fluid injection and what rate and what volumes is actually injected into particular regions. And this turns out to be one of the most difficult things to get, not because we can measure it, it's the easiest thing to measure because we have a pressure gauge on these wells, but a lot of the producing companies don't like to give that out because it tells their investors about the actual pressures in fields, what can be expected of those. So that's a real challenge for us, and that's why a lot of our research actually focuses in these geothermal areas where producing companies are much more willing to part with their data, or at least share their data and give us a better constraint of that. But we're building some very good connections with industry folks now, hoping to get their data and have an independent assessment of what's going on in some of these locales. So from these key pieces that I think are important of this, I want to focus on the precise earthquake locations, the fault geometry, and then also build that into the modeling portion that I do for my particular research. So what's really a huge advantage in recent years is on locating earthquakes. As I said, these can precede or come after significant events. They can be small magnitude seismicity at all times. If we have local seismic networks, we actually can detect down a magnitude of negative 0.5. Remember, it's on a log scale, so it can go negative. And the problem with just regular locations, as you see them on the USGS website, for example, is that these often are, the location uncertainty is often as large as 10 kilometers or so, especially in regions of the mid-continent where there aren't as many stations because they haven't had as much seismicity in the past. Much of this area is actually associated with the path the seismic waves take from the earthquake to your seismic recording stations. So one of the advantages is if you find two earthquakes that are close to one another, they travel more or less along the same path, and they'll have the same errors introduced by regions of low velocity or attenuation, whatever you may have, that are on those pathways of those waves. So if you find some of those that are close to one another, you can use those, locate the events again as a couple, and reduce your uncertainty, your relative uncertainty, down to about 10 to 100 meters or so, depending on your station coverage, data quality, and so on. The big challenge is that it's, sorry, go ahead.
When you're using that information and when you map the clusters, isn't that how you can find out that they were man-made earthquakes from hydrofrac or other man-made exploration in the region?
So these types of techniques are exploited also in these hydrofrac experiments where you actually try to track how far out your fractures grow. And now in those things, in those locations, you're actually talking about magnitudes of -2, -3, tiny events that track the opening of a fracture, basically the crack front as it grows away from your wellbore. So those are used to actually image how well you did and how far out these fractures grew from your well, and how much further you don't want to go to get into other rocks that could leak off. That's a very good question. So those techniques are heavily used in that. They stem from crustal earthquake seismology and are now used in industry applications quite extensively. But the challenge, and a good challenge, of course, is that there's a massive computational problem because any event could be recorded on several stations, many stations, and you have a lot of arrival times and do all these. So usually what you're solving for are billions of so-called cross correlations, and it's fun if you're into that sort of thing, which I know a lot of you guys probably are. So the results of that are on the top here are sort of the initial locations of a geothermal field where you have two productive regions. On the northeast, one cluster, and in the western, southwestern region. If we apply this, which we've done recently, you can really sharpen up these clouds of seismicity and actually detect structure and find faults in these regions. And a lot of these in this region are close to injection wells and production wells in this geothermal area. And so it does help you track some of the changes in physical parameters in a reservoir. So how do we go from now these clouds of earthquakes that we have of all sorts of magnitudes, how do we go to actual surfaces that we can use to build numerical models and understand the physics involved and how parameters that we can change effectively? So what you can do is you can exploit the fact that along fractures of any size or larger faults, you have a zone that's deformed around it because the stresses right at the surface of the fault are so large that you break rocks adjacent to it. And so if you look at this distribution of how events actually, how small events align, and this is normal to a particular fault, the central part would be the main fracture surface, and then you have additional deformation right around it. The largest number of events you have right along the center. And so you can use this distribution, which is not like a Gaussian distribution you may have heard of, or a Poissonian distribution, but it actually is a flat top. And it is a width that's related to a geological parameter, which is the width of the fault zone. And so we developed some algorithms or numerical techniques to use on the left here, these clouds of seismicity. This is the catalog of Joshua Tree to the Landers event. And I'm sorry they don't reproduce all that well in the small characters. And so if you use this event, that you can pick out now these aren't more events, they're just bigger dots that are plotted. You can pick out those that are most likely fall onto one continuous fault surface. And from that now, rather than just talking about dots in space and how many there are and how often they appear and how close they may be to injection or production wells, you can construct actual fault surfaces. So this is now taking these points, these earthquake locations that are the likeliest to be on the central portion of a fault, and you construct continuous surfaces from this. And with this, you can now construct a numerical model where you say, these are my surfaces, I know what the resolved stresses are somewhat well, or I can test out a range of parameters. I may or may not know what my friction is, but I can test that out. And it allows us to test what types of influence, if you now put a well close to it and you know what the the forces on those faults are, put a well close to it. If you get close enough to it, when could an earthquake happen? How large could it be? How close to failure are you? Now, this is not the same as saying we're predicting earthquakes, but we can predict the range of events that may happen. Anybody that tells you they can predict when an earthquake happens and how large it's going to be is a charlatan. So don't believe those things, but you can come up with ideas of what the ranges of event sizes are. And so finally, you get to the actual modeling portion of this. When you're solving slip on a fault, again, it's forces on the surface, and you get your critical state, and then you get slip. So part of my work at the USGS was to try to come up with a routine of how you actually allow slip on a surface, like this one up here, which is corrugated and has some undulations in both directions, but the general slip direction is in this way, so anisotropic in geometry. And you let this slip. Does it actually open? Does it create these open spaces along particular fractures that would reduce or allow more permeable reservoirs in a geothermal setting? And so we developed, now it's not quite KD equals F, which you may remember from even before you STEM type classes, where K is the stiffness of the material, D is the displacement, or the slip on the fault, and F is the forces that are acting on it. You have to constrain that it can only slip if friction is gotten to. And so it's a little bit more complicated than that, but it's these ingredients that you reformulate to suit your particular problem. And so we can test this and actually come up with, most of the slip is going to be down in this direction, but we have some significant heterogeneity, which helps. We also have opening, and to our knowledge, this is the first numerical code in at least your sciences that was able to predict these sorts of things in in a good way. So where we're going from this, of course, we're interested in the fluid flow and how injecting fluids into a fault or nearby a fault affect it. So now you don't just have to solve KD equals F. You also have to solve equations of fluid flow, which should be excited to see. So now you solve basically the heat equation and what it comes down to, which some of you may have seen in differential equations. So what is shown here is that you have the same fault at some point in time, and you have an injection well down at the bottom here that injects fluid at a particular pressure and some pressure history over time. And this fluid diffuses out along the fault and into the body, of course, that's surrounding it. And you have these pressure contours or pressure changes along the fault. If you couple the fluid flow now with the actual slip on the fault, you actually get, at certain points in time, depending on when you get to the critical state, that you slip this fault, and you get this shear displacement. And if you look closely, there is small displacement well out past regions where you've increased the pore pressure. So these problems are not quite as easy to say as we increase pore pressure, this is where an earthquake should be, but you actually can get larger earthquakes by infiltration of fluids only into a small portion of a fault. And again, you need to know what the attractions and so on, the forces that are acting on these faults. You need to know the friction, what happened before. So it's a complicated problem, and we're always lacking data, not just injection data. We're always lacking data because we just don't know what's going on with those faults. But these methods allow us to really sort of bracket the possible outcomes in regions where we have a good understanding. And so, conclusions to the scientific portion of the talk is that there's a good record of induced seismicity in the mid-continent. There certainly are some in California that we haven't cared so much about because we get bigger problems. Proper monitoring of both the seismicity, but also injection of fluids, pressures, volumes, and so on, should be part of the equation. So if an operator that records in any way, for their purposes, has those, they should share it at least with independent research facilities. And the modeling that we do and other folks do is becoming more and more sophisticated in being able to solve some of these questions and discerning what is induced and what is not induced. And there's obviously always a lot of debate over that. And you'll find a lot of production companies that say it's just natural tectonic seismicity. And this will give us better tools to prove them right or wrong. And again, we're data limited always. So that's something that we're probably never going to get over because you can't just dig out part of the crust and see what the fault's been. But so as far as conclusions that may be more interesting to you and that I sort of thought about in preparing this talk is what is sort of take home from the work I do and that you may do in the future if you're interested in this or similar things that are completely unrelated to earthquakes. And I think what comes up over and over again, even in fairly advanced modeling techniques or data analysis, whatever you want to do, the fundamentals you're learning now and the classes you take now, they will serve you for a long time. And they certainly have served me for a long time. And I'm glad that I took those. And I'm a big proponent of sampling other disciplines and trying other classes. There's a huge amount of overlap between different classes in different departments, and you can learn about what those types of methods or fundamentals and so on, how they're applied and how they benefit you. And I think the most important thing, if you don't take anything else away from it, is that having good fundamentals, having a good foundation in mathematics, physics, whatever field that it is you want to go in, that never goes out of style. And I still refer to some of my older books when I have to look up stuff. Of course, I'm starting to forget stuff now, so that may be part of it. So as far as advice, I look through the course catalog here and try to look for classes that I have taken and that I would take. Would I start again, and if I would embark on the same path? And there are a lot of great ones. Unfortunately, only one geology class. But there are really interesting topics, and you should definitely try to look for stuff outside of class, possibly. Obviously, CIS. Most everybody in sciences and technology will have to speak that language of computation. And whether you take C++ or Java, I don't really have a preference. They're both great. Engineering classes, of course, materials and so on are great. Math, of course, I think are probably the most crucial, along with physics. And I can't forget communication studies 110 that I hear you have to take also. Ideally the one by Professor Kaven. And my advice would be, at least to me, well, take as many as you can and find something that you're really passionate about. Don't just jump through hoops because that's the quickest way out, but find something you really like, because it certainly made studying for those classes easier for me, and I enjoyed it, unlike going to law school. And if you're interested in any of these careers, so whether it's earth sciences or engineering or whatever it is, get involved and do internships during the summer or throughout the year. There are a number of technology and engineering companies in the area. The USGS has a great internship program also. You can always volunteer, which may not be great because you don't get paid for it, but you learn a lot, and you just don't know where this is going to take you and how much you're actually going to learn and how you apply it in the real world. And so some of the opportunities, at least for earth sciences, and I'm sure there are millions more for other technology and science type of internships. USGS has a great program which is the NAGIT program, which actually stands for National Association of Geoscience Teachers. Yeah. Right. Yeah. Right. So they have a great program. We have about 10 or 12 NAGIT students every summer. They stay for 3, 6, 8 months. A lot of them stay for longer and actually get into some sort of employment. I'm not certain if they're paid, but I think there is some financial reward of that. If you're really interested in earthquakes, the Southern California Earthquake Center, which is a consortium of universities funded partially by the USGS, has an internship program that you can place at any major, or actually almost any university in California, I think is part of this. If you're more in the engineering part, and obviously there's a whole other bracket within the USGS that is thinking about the building response and building codes depending on what sort of ground that you're on. The Pacific Earthquake Engineering Research Center at Berkeley has paid internships also that you can apply for. And so I have the links for these up here. I believe the talk is being webcast and stored. That's the question.
Yeah. Are there any specific prerequisites for the internships?
I think you have to be a science major, so it depends on which one. So I just briefly read over the peer one. I think you have to be junior or senior, so it's maybe once you get to your AA and right before you transfer, that may be an option. I don't think for the NAGIT internship there is any problem. We actually have an intern in the audience who may have some more information for you, right? No? You don't? Walters?
Not anymore.
Not anymore.
Yeah.
But you have an alumni of the USGS volunteer and intern program in the audience, so ask him also. And so with that, thanks very much for your attention. I hope this was helpful.